Section 5.2, More Laws of Exponents in Scientific Notation. What do you do when you have x to the fourth raised to the third power? Well, we raise something to the third power by writing it down 3 times and then multiplying. So when you multiply, you add the exponents, so it's 4 plus 4 plus 4. That's x to the 12th. So what could we have done with the 4 and the 3? So we have the power rule of exponents. For any non-zero real number x and any integers a and b, x to the a raised to the b power is x to the a times b power. So when you have an exponent inside and outside the parentheses, you multiply those exponents together. So that gives us 2 to the third squared. We multiply the exponents, 2 to the sixth. 5 to the negative 2 squared, you multiply the exponents, 5 to the negative 4. Negative x to the fourth to the sixth. The negative is out front. Neither of the exponents apply to it. We have x to the, we need to multiply those exponents, 24th power. Y to the negative fourth to the 10th. Multiply those exponents, negative 40. X to the negative 3 to the negative 5th power. Multiply the exponents, x to the positive 15th power. What's the difference here? We have xy to the third power, and we have xy quantity to the third power. Here, what we really have is x times y times y times y. Only the y is being raised to the third power. The exponent applies only to the number or variable to its immediate left unless you have parentheses to tell you otherwise. So when you take the quantity xy and raise it to the third power, you're raising something to the third power, so you write it down 3 times and multiply. So really what you're doing is you're raising x to the third power, and you're also raising y to the third power. And raising a product to a power for any non-zero x real numbers, x and y, and any integer a, xy to the 8th power is x to the 8th power, y to the 8th power. So if you have a product inside the parentheses, you raise both factors, both x and y, to the power. So we have 2m to the 5th power. It's 2 to the 5th power, m to the 5th power. The parentheses tell you that the exponent applies to everything within the parentheses when there is a product in the parentheses. So we have negative 10 to the 4th power. What happens when you raise a negative number to an even power? It becomes positive. So 10 to the 4th, x to the 4th, and that's it. Notice that the negative was with the 10 in the parentheses. In our next example, the negative is not in the parentheses. It's waiting out front to make our answer negative. We still raise 10 to the 4th and x to the 4th, but this time it's negative because the negative was not in the parentheses. 3x cubed to the 4th. Well, we know that's 3 to the 4th, but it's x cubed to the 4th. What is our rule? When we have an exponent inside and outside the parentheses, we need to multiply. X to the 12th. a cubed, b to the 4th raised to the 7th power. We need to multiply the exponents both times. So it's a to the 21st, b to the 28th. Our next example has a -5, which the exponents do not apply to. It's out there waiting. It's negative. Our answer will have a -5 in it. But then we have x squared to the 6th. We need to multiply those exponents. And we also have y cubed to the 6th. We need to multiply those exponents. -2, we need to raise that to the 3rd power. What happens when you raise a negative number to an odd power? The answer is negative, and 2 to the 3rd is 8th. A to the 12th, and b to the 3rd. This time we're raising c to the 8th, d squared to the -5th power, so we need to multiply both of our exponents times -5. So it will be c to the -40, and it will be d to the -10. Many times when you work problems like this, you are asked to write the answer so that there are only positive exponents in your answer. Both of these have negative exponents, so we'll take them both down to the denominator to make them positive. So our next example, we have p to the -4, q to the 7th, r to the -2 to the 4th power. Let's raise everything to the 4th power, and of course we will multiply those exponents. We'll get a -16, we'll get q to the 28th, and finally we have r to the -8. Let's write our answer with positive exponents. So the q is positive, q to the +28. Leave it where it is. P to the 16th needs to go to the denominator, and r to the 8th needs to go to the denominator. What's our answer here? Take a moment, work this problem. What do you get? Do you get a 9? There's different ways you can do it. You could combine the m to the -7, m to the 3rd. You'd get m to the -4, and then multiply that times 2 if you want to. So we could have 9m to the -8, which would be 9 over m to the 8th. That's one way to do it. If you prefer, you can work this problem by taking the 9 times, go ahead and multiply the exponents, m to the -14th, m to the 6th, then combine the exponents. That still gives you m to the -8. So regardless of which way you do it, as long as you take legal steps, you will get the same answer. -4 to the -3rd power. When you raise a negative number to an odd exponent, the answer is negative. So -4 to the -3, x to the -3, y to the +6. Y has a positive exponent. Leave it alone. Our answer is negative. And let's go ahead and take that 4 to the -3 to the denominator, and x to the -3 to the denominator, and that's our answer. Be careful. The thing that people want to do with exponents sometimes is they want to take the negative in front of the number and the negative exponent, and they think somehow that those should cancel. They do not cancel. The negative in front is large, it's in front of the number, it indicates value. The answer is negative. The negative 3 exponent is small, it's up high, and it indicates location. Negative exponents indicate location. They never cancel each other. You get rid of negative exponents by placing them in the correct position within the fraction. Negative exponents indicate location. So finally, we have x squared over y cubed squared. How do you square a number? Well, you write it down twice, and you multiply it, even if it's a fraction. So if you multiply these, you get x to the 4th over y to the 6th. Now look back at our original problem. What could we have done with the exponents? We found out before that if you have exponents inside and outside, and you have a product inside the parentheses, you just apply the exponents to both factors, or all factors. Do you suppose we have a rule now about quotients? Adding a quotient to a power. For any non-zero real numbers, x and y, and any integer a, if you raise the quotient x over y to the 8th power, you can just individually raise the numerator to the 8th power and the denominator to the 8th power. So it's kind of similar to the product rule. We can now raise a quotient to a power. So we know that if we have x over 2 to the 5th, we have x to the 5th divided by 2 to the 5th. If you raise negative m over n to the 4th power, in fact, if you raise any negative number to an even power, your answer will be positive. So we have m to the 4th over n to the 4th. Here we have a negative number raised to the 3rd power. We're just bringing that exponent in and applying it to all the factors in the numerator and all the factors in the denominator. So we have negative 2 cubed, which is negative 8. We have x to the 9th. We want to multiply those exponents. We have y cubed, and we have z to what power? 15. The 15th power. What's going to happen if we have 2 over x to the negative 3rd power? Well, using our quotient rule, we'll have 2 to the negative 3 over x to the negative 3. Negative exponents indicate location, so let's make that x to the positive 3 over 2 to the positive 3. Look, what did that negative exponent do to the fraction? It flipped that fraction. If you take x over 2 to the 3rd, you get x to the 3rd over 2 to the 3rd. So the negative exponent flipped the fraction. Raising a quotient to a negative power for any non-zero real numbers, x and y and any integer a, x over y to the negative a is the same thing as y over x to the a. So if you raise a fraction to a negative exponent, it flips the fraction. So let's take this fraction, negative a over 5, we're raising it to a negative 2 exponent. So the first thing we're going to do is we're just going to flip that fraction. It's still negative, but we flipped it. We can then make the exponent positive. Flip the fraction, make the exponent positive. So when you raise a negative number to an even power, it makes the answer positive. So we have 25 over a squared. Here, our next example, the negative is out front. It is waiting to make our answer negative. So let's figure out what that negative exponent is doing to our fraction. It's going to flip that fraction. 2y to the 3rd over x to the 4th. And then that is being raised to the 5th power. So now let's use the exponent and do what we need to do. We have 2 to the 5th, y to the 15th, x to the 20th. This example, 3a squared b to the negative 4 to the 3rd power, there are different ways that we can approach this. We could just go ahead and apply our exponent outside. So we'll get 3 to the 3rd, a to the 6th, b to the negative 12. And then let's rewrite our answer so we only have positive exponents. 3 to the 3rd is 27, so I'm going to go ahead and write that as 27. A to the 6th, take the b to the numerator, and it's b to the positive 12. Our next example, we're raising a negative number to a 5th power, so we know our answer will be negative. There are different ways to approach it. I kind of favor simplifying. What is x cubed over x? I'd like to go ahead and make that x squared, using our subtraction rule, our division rule of exponents. What about y squared over y to the 5th? I personally would like to go ahead and simplify that and get y cubed, and then raise it to the 5th power. You can go ahead and raise it all to the 5th power and then simplify, but I prefer to do it this way. So our answer is negative. We now can apply our outside exponent, so it's x to the 10th over y to the 15th. Our next example has a negative exponent applied to a fraction. The negative number is outside, ready to make your answer negative, but we need to flip that fraction because that negative exponent has the effect of flipping the fraction. That's not the only way you can work this problem. You could just go ahead and apply that negative exponent to everything, but we're using our rule that we had for fractions. So we have a negative. Let's apply that 2 now. Our exponent is a positive 2, so it's d to the 20th, e to the negative 16 over 8 squared is 64, c to the negative 6. And let's go ahead and straighten up our answer a little bit by making all of our exponents positive. D to the 20th, 64 is in the right location, but c to the negative 6 has to move. Becomes c to the positive 6 in the numerator. And e has to move to the denominator, e to the positive 16. Scientific notation. Scientific notation is used to represent very large and very small numbers. A number is in scientific notation if it is written in the form a times 10 to the nth power, where n is an integer and a is greater than or equal to 1 but less than 10. It's very important that a be between 1 and 10. It can be equal to 1, but it cannot be equal to 10. It must be less than 10. So let's look at the next page for our examples. The distance from Pluto to Earth, that is a very large number. 2,670,000,000 miles. I would rather write that as 2.67, a number between 1 and 10, times 10 to the 9th power. What about the width of a strand of DNA? That is a very tiny number, 0.00000000013 meters. I would rather see that number written as 1.3 times 10 to the negative 10. Notice that large numbers, like the distance from Pluto to Earth, when you look at the power that 10 is raised to, it is a positive exponent. And when you look at small numbers, such as the width of a strand of DNA, and you look at the exponent that 10 is raised to, it is negative. Large numbers have positive exponents, small numbers have negative exponents. Let's express these numbers in scientific notation. Where is the decimal currently in the number 8,130,000? Currently, it's to the right of the 0. It's not written, but it's understood to be there. Where do we have to move the decimal so that we have a number between 1 and 10? The only place that you can move the decimal and get a number that's between 1 and 10 is between the 8 and the 1. So our answer will be 8.13 times 10. This is a large number, so we're going to raise the decimal, raise 10 to a positive exponent. The question is, how many places did we move the decimal when we moved from the original position to the final position? How many places over did we move the decimal? 6 places. So our final answer is 8.13 times 10 to the 6th. This is a very small number, so when we write it in scientific notation, our 10 will be raised to a negative exponent. The decimal is currently between the two zeros here. Where is the one and only place that we can move the decimal so that we will have a number between 1 and 10? It has to be between the 3 and the 0. How many places do we move the decimal from its original location to the location where we know it has to be? It has to move 3 places. That will give us 3.042 times 10 to the negative 3. The exponent is negative because it is a small number. 4.25. The decimal is currently, in our scientific notation, between the 4 and the 2. The exponent, 5, tells us that we have to move the exponent, or the decimal, 5 places. It's a positive 5, so we know this is a large number. If we move the decimal to the left, it will make it small. It will make it a small number. We have to move the decimal to the right 5 places. It starts off here between the 4 and the 2. 1, 2, 3, 4, 5. The decimal has to be here. We don't have anything in these locations. We're saying we have to move the decimal there, but there's no numbers there. We have to put zeros to hold the place. So our number is actually 425,000. It's a positive exponent. It's a large answer. And we move the decimal 5 places. This number has a negative exponent, so it is a small number. The decimal is originally here between the 1 and the 0. We have to move it 4 places, and we know it's a small number. If we move the decimal to the right, it will make it bigger. We need to move the decimal to the left. 1, 2, 3, 4 places. So the decimal will end up here. Notice once again, we've moved it past the point where we have digits. We have to have some digit here to hold the place. Let's put a 0 in those locations to show, and you might want to put a 0 to the left of the decimal, to show that our answer is 0.0001073. What is that? That's tenths, hundredths, thousandths, 10,000ths, 100,000ths, millionths, 10 millionths. So it's 1,073 10 millionths. I'd much rather have it in scientific notation. So on a calculator, the number 3.12 times 10 to the 25th is often written 3.12e or EE25. So if your calculator has a number and it has an E in it, that means it's in scientific notation. And the number to the right of the E is the power to which 10 is raised. So 2.9e negative 14 means 2.9 times 10 to the negative 14th. These numbers in the following examples are not expressed in proper scientific notation. Can you tell why? Look at that number, 23.6. We said that the number had to be between 1 and 10. That number is bigger than 10. We can't have that. There are different ways to approach this. The way I like to think of it is to think of it as 2.36. I like to take that 23.6, which is a large number. I move the decimal one place, so it's times 10 to the positive 1, and I still have 10 to the positive 6. And then I can combine those powers of 10. So 2.36 times 10 to the 7th. What about this 0.3 times 10 to the 5th? What's wrong with this number? It's not in proper scientific notation. 0.3, is that a number between 1 and 10? No, it's not. 0.3 is a small number, so I'm going to move the decimal until I have a number between 1 and 10. I have to move it one place to the right. It's a small number, so that's 3 times 10 to the negative 1 times 10 to the 5. And then I can combine those powers of 10. I add the exponents, and so I get 10 to the 4th. What's wrong with this example, B? That number is not between 1 and 10. We have to move the decimal to make it a number between 1 and 10. 5.6. Notice 5.56 is a small number, so it's times 10 to the negative 1 times 10 to the negative 6. So our final answer will be 5.6 times 10 to the negative 7. What about 370? That's way too big. That's a big number. Where do you move the decimal so that you have a number between 1 and 10? 3.7. How many places did we move the decimal? 370 is a large number. We moved the decimal 2 places, and we still have times 10 to the negative 4. So now we can combine our powers of 10, 10 to the negative 2. 3.7 times 10 to the negative 2. So when numbers are in scientific notation, they're easier to calculate. So we can calculate very large and very small numbers very easily. So when we're multiplying this first example A, we have 3 times 10 to the 4th times 2 times 10 to the 9th. We know that multiplication is commutative. You can change it, the order in which you multiply. So how about we multiply the 3 times the 2? That will give us 6. And how about let's go ahead and multiply the 10 to the 4th times the 10 to the 9th. That will give us 10 to what power? 13. 3.8 times 10 to the 11th. 6.5 times 10 to the negative 2. Once again, let's change the order in which we're multiplying. Let's multiply those numbers together first. 3.8 times 6.5. That's 24.7. Now let's multiply our powers of 10 together. 10 to the 11th times 10 to the negative 2. Add those exponents and you get 10 to the 9th. Is this our final answer? Is it in scientific notation? 24.7 is not a number between 1 and 10. It's a large number, so we're going to change it to 2.47 times 10. We moved the decimal one place, and we still have times 10 to the 9th. So our final answer will be 2.47 times 10 to the 10th power. Let's multiply the 8.7 and the 4. That gives us 34.8. Let's multiply our 10 to the negative 5 times 10 to the negative 8. We add the exponents. That gives us 10 to the negative 13. Our answer is not in proper scientific notation because this number is not between 0 or between 1 and 10. So, let's make it a number between 1 and 10. Let's change it to 3.48. 34.8 was a large number. We moved the decimal one place, so that gives us times 10 to the 1st, and we still have 10 to the negative 13. 33.48 times 10. What do you do to those exponents? You add them, and that gives us our final answer. What about division? I prefer to write problems like this as a fraction. 5.6 times 10 to the negative 2 divided by 2.5 times 10 to the 5th. So, in the order of operations, multiplication and division are an equal footing. We can go ahead and divide the 5.6 by the 2.5, and that will give us 2.24. Now let's handle our exponents. What do you do with the exponents when you're dividing? You subtract. So 10 to the negative 2 minus 5 is 10 to the negative 7. We're fine with negative exponents in scientific notation because it tells us whether the number is large or small. Negative exponents means you have a small number. Last example. Once again, I'd prefer to write this as a fraction. So 3.0 times 10 to the negative 8 divided by 6.0 times 10 to the negative 3. What's 3.03 divided by 6? That's 1/2, which is 0.5. 10 to the negative 8 to the negative 3, you need to subtract those exponents. What is negative 8 minus a negative 3? That's negative 8 plus 3, that's negative 5. Is this our final answer? Is it in scientific notation? No. This number is not greater than 1. So we need to change it to a number between 1 and 10. It was a small number. We moved the decimal one place, so it makes it times 10 to the negative 1 times 10 to the negative 5. So that gives us 5 times 10 to the negative 6. And that's our answer. Light from the sun traveling at a rate of 300,000 kilometers per second reaches Earth in 499 seconds. Find the distance expressed in scientific notation from the sun to the Earth. Now we know that distance is rate times time. The rate at which light travels is 300,000 kilometers per second. The time that it takes to reach the Earth is 499 seconds. Notice those seconds cancel and leave us with kilometers. So we have 300,000 times 499. We can go ahead and just put this in our calculator. Most calculators can handle that. Or we could convert our numbers, our answers, to scientific notation. 300,000 is 3 times 10 to the 5th power. 4.99 times 10 to the 2nd power. We move the decimal 2 places. So 3 times 4.99, that's 14.97. And what about our powers of 10? 10 to the 5th, 10 squared, 10 to the 7th. This is not in scientific notation. 14 is a large number, but we need to make it a number between 1 and 10. We'll move the decimal between the 1 and the 4, so 1.497 times 10 to the 1st times 10 to the 7th. So it's 1.497 times 10 to the 8th. And remember to always put your unit of measurement, it's in kilometers. 1.497 times 10 to the 8th kilometers. And that's our answer. That's all for this section.